Okay, good morning everyone, and thank you for being here with me in the morning today for my talk, Understanding the Microsoft Office 2013 Protected View Sandbox. So, a little bit about myself. My first name is Chuan, but my friends call me Yong for short, and Ko is the last name. And I am a security consultant with MWR Info Security in Singapore. Normally for work, I do things ranging from source code review to binary and malware analysis. And on top of that, I get to do some research in my own time. And that is why I could be here sharing today. Personally, I am interested in reverse engineering in general, vulnerability research, and also does a little bit of exploitation on Windows. So here is the outline for today's talk. I will begin with a brief introduction of the Protected View Sandbox. This will be followed by a section about its internals, which would include the architecture, the initialization process, and the sandbox restrictions. Next, in the IPC section, I will talk about the internal objects that the broker use during IPC and the format of the IPC messages, and after which I will highlight the purpose of some of these messages. And since the Office 2016 preview version has been released, I will make a short comparison and see what has or has not changed. And lastly, of course, I will end this talk with the conclusion. And now the introduction. Okay, before we begin, let us define what is sandboxing, as Wiki defines it as. A sandbox is a security mechanism for separating running programs. A sandbox typically provides a tightly controlled set of resources for guest programs to run in, such as scratch this on space, blah, blah, blah. A sandbox is implemented by executing the software in a restricted operating system environment, thus controlling the resources that a process may use. So this kind of suggests that imposing restrictions on application resources is central to sandboxing. But what kind of resources are we talking about here? It could be as simple as the file systems or registries to process-related actions like token duplications or creating new process. But as a side effect of the restrictions, sometimes there are certain actions or events that the sandbox should be allowed to do but are prevented to do so. So in practice, there is usually a predefined set of tasks that the broker can do on its behalf if the broker asks for them. The Protected View Sandbox is a feature that's introduced since MS Office 2010, and unlike typical sandboxes, the Protected View Sandbox is not used to render all the files. Instead, it's used only for files that Microsoft defines as untrusted. And this largely covers files that originate from the internet, such as those that are downloaded or those that are as Outlook attachments. So in general, the Protected View will show the file in a read-only text view mode, while at the same time it disables other unnecessary features for this purpose. Now, the motivation for this research arises because at present, there are many excellent research on sandboxing used in other applications. For example, Mark Vincent Jensen's and James Forshaw's work are often referenced for IEPM. But as of now, although the Protected View has been present for 5 years, there is no public research on it yet. And besides, Microsoft did not release any technical information about this sandbox either. So going back to the definition of sandboxing, the objective of the research should be to find out the sandbox restrictions on the Protected View feature, and also the list of tasks that the broker could do for the sandbox, i.e. the IPC messages. And a white paper will eventually be released together with this slide, so refer to it for more details if you want to. And for the audience that are expecting a 0 day from this talk, I would like to apologize in advance. So moving on in this section, I will talk about the sandbox internals, which will include how we will draft the architecture, and we'll also talk about the startup process and also the system resource restrictions. And since there is no public information, the Protected View Sandbox model will be determined by comparison against the IE model. And the IE model is chosen mainly because of the likelihood of code reuse in Microsoft, or they may at least share similar components. and also because there's good reference for it because it's extensive research by many other researchers. Now, this is a typical IE sandbox architecture consisting of a higher privilege broker process. The sandbox process where the web content is to be rendered in and also the OS. In this model, three main components are central to the functionality of sandboxing. The first is the intersection component. Second is the elevation policy component. And lastly, of course, we have the IPC. The intersection component is used to redirect API calls. In IE, this redirection facilitates three purposes. First, it can modify the API parameters for the sandbox context. So, for example, original file path which would have points to outside the sandbox container will be changed by this redirection so that it will point to inside the sandbox directory. And second, there may be certain situations or actions that may simply need to be performed in the context of the broker. And lastly, the redirection may be forwarded to the elevation policy component, for which the administrator can configure on its launch behavior. The intersection client is achieved by API hooking, and in the case of IE, it's done by patching the IAT. So to find out whether the protected view has a similar component, the IAT of the sandbox process was used for patching, was checked for patching. And in addition, the EAT and the function prologues of all the modules loaded are also checked. And as it turns out, there's no patching in these three areas. So there don't seem to be an intersection component present here. And since the intersection component is not present, it is likely that the elevation policy will not be present as well, since both are related. But nonetheless, we will still do another check, but this time from another perspective. Now, we know that the elevation policies are stored as registry keys in the application name, application path, CLSID, and launch policy value format. And the manager will check this register to decide whether the requested process or COM should be started. Therefore, our check would involve first filtering out the new registry keys introduced between Office 2007 and Office 2013. And from this, we check whether they have a similar key value format. Office 2007 is chosen because that's the last version that does not implement the protected view feature. So this means that any new registry keys introduced could possibly be related to the sandbox. And as it turns out, none of the new keys had this format, and so we conclude that there's no elevation policy component either. Lastly, the IPC is a fundamental component in any sandboxing implementation, because somehow, for various reasons, the sandbox will need to talk to the broker at some point in time. Unsurprisingly, this component is present in the protected views implementation. But unlike the IE, where both COM IPC and shared memory IPC are used, the protected view sandboxing uses only the NIM-pipe IPC. And this mechanism will be discussed in more details in the next section. So the final protected view sandbox model is actually very simple and should look something like this without the two components. This is hardly surprising given that this feature is intended to show only a text view of the file, and therefore all the full functionalities of the application are not needed. This also means that the attack surface for sandbox escapes are greatly reduced, and especially so for the absence of elevation policy, which has been commonly abused in IE-EPM escapes. As a final note here, you see that all untrusted files are rendered in the same sandbox process. So therefore, the broker will need to find a way to identify each file. And we can see how it does so from the internal objects that we talk about later. Now, in any sandboxing implementation, there are three factors that should be considered during the creation of the sandbox process. First, it should have a restricted access token, either by assigning or dropping the appropriate seeds, or in the app container case, the capability seeds. Secondly, the sandbox process should be created in an isolated Windows station and desktop to minimize the interaction it may have with other processes. And finally, its process behavior should also be restricted with its job handler. Now we will look at the solid process and at the same time check whether these three factors are applied. So here is the flow chart. There are two modes of which the sandbox can be started in: the low incredulity mode if it is in Win7, or app container mode if it is in Win8 and above. The broker will discover this environment by either checking the HKLM software, Microsoft Office, common security user app container registry key, or whether calling these two APIs will succeed. The orange boxes will represent the differences in startup between these two modes. The green boxes will represent the differences due to application settings. For a start, we see that each sandbox name is randomized by only the last 10 bits. Then it sets the restrictions for this job object. But it does not do this all the time, and by default, there's no UI restrictions at all. Next, it generates the sandbox seed accordingly. In the app container mode, this is done with the derived app container seed from app container name API, and in the integrity mode, the sandbox seed is hard-coded but for the last 4 digits, which is reused from the sandbox name. Next, the broker will disable, restrict, and allow these respective seeds from the sandbox token if it is in the integrity mode. And lastly, it sets the low integrity level. And next, the broker creates the sandbox directory and grants the access. In the app container mode, the access is granted only to the sandbox seed, while in the other mode, the respective seeds are granted individually. The broker then creates an isolated desktop if needed to, but by default, this is not the case, and therefore, the process is created in the default desktop. Next is set up the IPC name pipe with a buffer size of 2000 bytes. In the app container mode, the broker will add the Office capability seed before starting the sandbox with the create process as user API. So in this flowchart, we see that the process by default is not created with desktop isolation and also job UI restrictions. So what this means is that the protected view process is still affected by these known IEEPM issues, which are reading and writing to the clipboard or doing screen captures. Now, I'm sure many knows that the app container is largely based on a concept known as capability, which will in turn define the system resources that the sandbox can access. In IE, these capabilities are known and defined either in winnt.h or from the capability mappings registry key. But as you can see from the startup flowchart, the protected view sandbox is assigned only one capability, which is not documented or defined publicly. So to define the boundary of the sandbox container, we will check for the sandbox and capability seeds in the access control list in an iteration of file locations and registry keys. For the file locations, with the sandbox seed, the sandbox will actually access only the user profile app data, local packages, directories, and subdirectories with the standard writes all access. The capability set does not allow access to any file locations, and this result is what we would have expected as seen from the startup process. For the registry keys, the sandbox seed could access these sandbox-related keys with mostly key or access rights. For the capability seed, only Office-related keys could be accessed, and with only the key read rights. Among these is the current user software Microsoft Office Word Security Trusted Locations key, which would have defined the file path for which the protected view mode is to be excluded. So meaning that if somehow you could put the file path of your own file into this registry, then it will not be open in protected view. Another slightly interesting things which you can read from the Office registry key is the file MRU subkeys, which will contain the files that are recently opened in Office. Finally, the capability set does not allow outgoing connections to be made from the sandbox, as it will fail with permission denied on connect. So putting everything together from the internal section, you have this final illustration. The first new addition is at the lower left, where the sandbox can make API calls relating only to its own directory and registry, and also the Office registry keys, but with key read rights. And with no desktop isolation and job UI restrictions, it could actually interact with other processors sharing the same desktop for effects such as accessing their clipboards or using the user handles of other processors. Finally, it cannot make connections out to the internet. So in this section, I will talk about the IPC mechanism that the protected view sandbox uses, which is always an attractive vector to look at for security issues. I will first begin with the internal objects that the broker use, followed by the format, and lastly, I will highlight some of the messages. So this is an overview of the objects that the broker uses for the protected view feature. And it all starts with the threat manager object, which will hold reference to the IPC message sensitive, view restrictions, and view manager objects. The IPC message sensitive will describe the status of the IPC name pipe and also contain the buffer that it reads or writes to. The IPC view restrictions will contain information from the sandbox startup process. And the view manager is actually the one of interest here. It mainly contains 4 sets of threat manager and view tracker pointers. I'm not exactly sure why there are 4 sets of pointers, but from what I have seen, the last 3 sets are null. Otherwise, it doesn't seem to serve much purpose other than as a placeholder object. So recall earlier when I said that because all untrusted files are rendered in the same process, the broker will need to find a way to maintain a state for each file. So this actually starts from the view tracker object, where it holds an overview of the sandboxing state. So an example is the num view file field, which will show the total number of untrusted files currently open. The view tracker would also hold a pointer to a dynamic array of view file objects. Each view file and all the subsequent objects are used to represent and contain information for each untrusted files. This is a more detailed view of the threat manager, and view tracker objects. Also showing the offset of each field, the size, and some comments for them. In each object, some fields are missing because they are either irrelevant to be shown here or they are simply unknown. And these are the corresponding details for the view file, same broker app, and wwlib IPC message objects. Here you can see more clearly that the view file object contains information about the individual files. And in particular, the view ID is important because it identifies each file, starting with a value of 1 for the first one. And this field is commonly used in many IPC requests for the broker to fetch the corresponding view file object. The same broker app is not always present, and it depends on which process opens the file. In the illustration on the top right, if the sandbox has Outlook as its parent, as shown by 1B, 2A, and 2B, then this object will not be created. And in each case, the wwlib IPC message will be missing as well. And as a side note, the global variable at 015E9A9C would show this situation as well. In general, all these 3 objects contain fields that are referenced directly by the respective IPC message. So the message could be as simple as asking for the file name for a specific view ID. And these IPC messages can be broadly classified in 2 groups, depending on whether it is handled in mso.dll or wwlib.dll. Another observation from this is that with the Outlook broker situation, the wwlib and a subgroup of MSO IPC messages will not be available. In general, the format of IPC message will consist of a header and body, which is optional in some cases. The header for the MSO and wwlib groups will differ slightly. Their common fields would be the message tag, which will identify the type of message, the message ID, which will pair the request and the response together, and also the message size, which theoretically should have a maximum size of 2,000, as we have seen from the pipe creation. The view ID field is unique to the wwlib group of message. And the header for the response is similar except for the first field, which should now show the status of the request instead. These 2 functions are found in MSO and wwlib, and are where the broker would service each IPC request in the purple blocks here. And before every purple block, a format check on the message is done on the pink blocks. The format check will include things like whether the size is correct, by comparing the size field in the header with the total bytes received. Or in some cases, some IPC message actually has a fixed message size, so the format check will include that as well. Or it could check the length of string-related fields or to update any string pointers. So now we will look at some IPC requests, starting with the 001. This request has no message body, and all it does is for the broker to duplicate and return the current user software policies registry key with key rate access without keeping account of the duplications. And it is implemented as a workaround to the Sandbox registry key restrictions. This software policies key is usually used to define application policies as part of the group policy administrations. And next, we will look at the 061 request, which has the parameters for the post message API in the message body. So we may think of using this 061 request to post a number of messages to disable the protected view in two scenarios. First, we could try to navigate to the File tab to enable editing with the keyboard inputs as shown on the left snapshot. But this would have failed because in order to post message, the Sandbox window has to be in focus, which is not the case after the navigation. So this brings us to the second scenario. And since it has to be in focus, we might want to try brute forcing the screen coordinates and then send mouse click to enable editing directly. But this is also not allowed because the mouse click value is not accepted in the DW message parameter for this request. Now, although most features are disabled in protected view, URLs are still accessible from the untrusted file, and the 091 message is a request for this purpose. It will request the broker to navigate to the URL with the hlink navigate to string reference API, pending user permission. And this permission will be asked per file per session and will be stored in the view file object session enable hyperlinks field. The 081 message is a request for the broker to create the enter password message box for a password protected file, for which the input is to be returned to the Sandbox. This message is an example of a request that is serviced only when the same broker app is missing, as in the case when the broker is Outlook. The reason for this is because the Outlook does not do any file parsing itself. So right when a file attachment is open, it will start the Sandbox process immediately and ask the Sandbox to handle the file. So while handling the file, the Sandbox will then realize that it needs a password, and therefore it will send this request for the Outlook to prompt the user. So this is in contrast to the case when the broker is a Winward, and the broker would prompt the user for the password before the Sandbox is started. So in the Outlook broker case, because it does not track the situation itself, it will always create a new worker object for the password prompt even after the file is open, as you can see from this last snapshot where the file is already open in the background. So I'm not really sure whether this behavior is intended or not. Next, we will look at the 0C1 message, which is an error reporting request. In a typical Windows error reporting scenario, the application that's in trouble will create dwin on itself and passes to it the exception information, such as defaulting EIP. But in the case of protected view, the Sandbox cannot do so due to the job restrictions. And therefore, it will use the 0C1 request so that the broker can create dwin on its behalf. And because each IPC message is limited to 2,000 bytes, the Sandbox will pass to the broker this exception information with a shared memory instead, as shown by the Sandbox shared memory handler in the format table. Subsequently, the broker will then pass this information to dwin in the shared memory mode with the broker shared memory handler. And this is the format of the memory that the broker will share with dwin. Two parts of this shared memory are highlighted here. In the first box, the WER submit file list is a list of full path files that are to be submitted to the WER server. One of these files, the additional WER file name, is to be specified by the sandbox as part of the IPC request. The second box is a chunk of parameters for which the dwin will use for the WER report, and is set by the sandbox in the sandbox shared memory. But before we go on, let's take a short look at what happens during a typical Windows error reporting. When an error occurs, the user will have three options: check online for a solution, close the program, or debug the program. If he chose the first option, then dwin will send the level 1 error reporting data to the WER server. This level 1 data will contain an overview of the error, like the OS version, application version, exception information, and also files related to this error in an XML format. At the server end, it will decide whether this error is interesting enough or unique in its database. And if it is interesting enough, then it will ask the application for level 2 data, which would consist of the files that I mentioned earlier. And these files are compressed in a .cap package. After sending, dwin will clean up by deleting these files in the local system. So there are two issues relating to the 0C1 message. The first one is a read access violation when the broker tries to copy a fixed size of 15F0 bytes from the sandbox shared memory to the broker shared memory. This chunk of bytes are to be used as parameters for the WER report create and WER set parameter APIs. But during the copy, the broker did not check whether there is sufficient size to copy from in the sandbox memory. The second issue allows the sandbox to trick the broker to traverse out of the sandbox container. As mentioned earlier, with the additional WER file name field, the sandbox can set one of the files in a .cap package for level 2 data. But this field will by right contain only the file name because the broker will have first checked that there are no / character before prepending the sandbox directory for its full path name. So the whole purpose for this is to ensure that this file is located in the sandbox container. And the snapshot here shows the broker checking only the / character. But if you were to look at MSDN, it will state that in file IO APIs, internally it will convert the / in the file path to /. So in other words, if you use / in the additional WER file name, this would have allowed us to bypass the name check by the broker and upload any local files. So at this point, I can show a small demo. Okay, so effectively what we do here is to inject a DLL into the sandbox process. And all this DLL does is to send a 0C1 message. With the name pipe. So are these the parameters? Yeah, no. Okay. So these are the parameters for the 0C1 message, and these are the fields for the message body. The DLL will also create the sandbox shared memory, and shown by the functions here. So if you want to check the issue one mentioned just now, you can decrease the size of this memory size and play around with it. So effectively what we are interested in is this line, this field here. And this actually allows us to traverse out of the Sandbox container onto the desktop and then tries to upload this text file here. Okay. This is just to inject the DLL into a Sandbox process. And with regards to error reporting, you can either send the report back to the Microsoft server, or you can specify a corporate error server in your corporate environment. And since you don't want to send anything back, we will do via the corporate reporting route here. So you just specify the IP over here, and this is actually our server here. So I'm going to just check the IP. Okay. Okay. So let's inject the DLL. 3444. Okay. Check online to send level 1 data. Okay. So the level 1 data contains the XML, which should look like this. And this would tell the server the OS version, application version, and also the exception information. And this will be the files that will be sent back in level 2. So the server will send this response back to us for level 2 data. And before sending, the user will need to grant the permission to do so. And if you see the list of files that are to be uploaded, we see that this is actually what we specify, prepended by the Sandbox directories here. Okay. So we will send. Yep. And this will be deleted. And it should be appearing here. Yep. So these are found on the desktop. So essentially, we could upload any file to the server, which by default points to watson.microsoft.com, or to a pre-configured enterprise server. Alternatively, we could also use dwin to delete any file, as it does so after sending the .cat package. So this issue was reported, and the response was that it does not meet the bug bar for servicing, but will be fixed in future. And so we will see if this is still present in Office 2016. The last IPC message we'll talk about is the 0F1 request. It's actually a Microsoft help message that either creates the clv.exe or would navigate to the developer help website, depending on the request parameters. And like the 0C1 message, there's also a read AV here, and this time because of a null dereference. So in the last section of today's talk, we will check whether there are any changes made to the Sandbox model in the preview version of Office 2016. In terms of the code, there are two main changes. First, common routines are moved to new individual modules, such as the MSO20 Win32 client.dlls. And secondly, security assertions new to Windows 8 are also added. In terms of the Sandbox restrictions, no additional capability seats are assigned. So what this means is that there should not be any changes to the system resources that the Sandbox could access. Next, most of the startup process has remained the same, except for the addition of a create process code block before starting the Sandbox process. So this additional option looks a bit weird because currently there doesn't seem any way that we can change the conditional byte at EB1 plus 81, EBX plus 81 to cause the branch into create process. So maybe this is related to a future option for protected view. So here we look at the 0C1 message again. And personally, I'm curious because since the time they responded to me to the time of 2016 release, there's actually 2.5 months to add a few lines of code to check for the /. So if you compare the snapshot on the left with the one on the right, you can see that there is no change for the name check yet. So obviously, this is among one of their least priority issues to do. But I can understand that because to trigger this would first require a code execution in the sandbox, and then the user interaction is also required to send the file back to the WER server, and also to delete it. So the 161 message is a new request introduced in 2016, and it will be serviced only if the Outlook is loaded by, the sandbox is loaded by Outlook. So it's a very simple request to protect or unprotect the sandbox window for rights management protected files. And finally, this all request has a new message size, but otherwise nothing else has changed. So in conclusion, the Protected View Sandbox does not aim to offer full functionalities of the original application. Therefore, it can do away with the intersection and elevation policy components to implement a very simple model. This approach also means that the number of supporting IPC requests are greatly reduced. And as a comparison, the Adobe Reader has about 200 plus IPC message compared to the 38 in Protected View. Even so, like with all software, some issues are still found. For example, the desktop isolation and the job UI restrictions are not applied by default. And this has been present since the IEPM. Code quality-wise, Microsoft has been careful in dealing with the buffer sizes and so on. But to-read access violations are still found, even though their impact is minimum. And there's also the directory traversal issue, which is not fixed yet. If you were to use the 2016 as a glimpse to how the sandbox may evolve, it is likely that there will not be much changes, but I personally is curious to know how the new create process option will be used. All in all, I think that this feature still offers quite a good sandbox protection to users. Here is a subset of the reference, and this is the end of my talk. Thank you.